Week 3. Here we go. We're focused on probability. So how likely is something to happen? Is it likely? Is it unlikely? Is it always? In statistics, most that we're looking at is based on probability, which is why we're solely focusing on just the foundation of probability for this lecture. The probability of something when it comes to this class and in general with stats is usually with a capital P or with whatever it is that is being what the probability is in between. So for instance, in this, it is the probability of event A. It would be PR parentheses A. If it's probability of event B, there would be a B in there. So an event is the outcome or the set of outcomes based on random variables. So let's just remind ourselves that within the probability of something, everything should be focused around that it was randomized. So why do we learn about probability? In summary, anytime we want to answer a research question that involves using a sample to draw a conclusion about larger population, which is inferential statistics, we need to answer that question of like, how likely is it? Or what is the probability of something? And to answer that question, we need to understand the probability rules, and the models that come along with it. So with that, there's the slide itself. So probability permits us to deal with random variability in a positive way, in a constructive way, and it is to accept the existence of chance within just the natural world. So what's amazing is that what probability and what we're going to go over, this is found throughout all of nature. It's pretty interesting, actually. I know, it's math, yay. So to use probability in everyday life, you always make judgments around probability. Like, everything is really probability when it comes to making an action. So here are some examples. I'll just skim a few. So I want to ride my bike, so what is the probability that it's going to rain today? Well, is it a 60% chance, an 80% chance, a 20% chance? Those things make you change your behavior based on that probability. What song would come up on shuffle, out of random, even though I have a belief that there's a little bit more to anything, say, on Spotify or something else. Should I get the $500 deductible or the $1,500 deductible on my insurance? What's the probability of me getting sick? Personally, for me, I've had a lot of medical history, so I like to take my chances and go for the lower deductible, which is usually cheaper insurance. So there's some examples to just kind of get your brain rolling. I'm going to breeze over this part real quickly, but you need to know that there are two types of interpretations of probability. There's the frequentist interpretation, and then there's the Bayesian interpretation. And both of these, they follow the basic general same rules. However, Bayesian is kind of just a little bit more modern in the idea that it takes into account that by every other individual also looking at the same probability, it considers that. So we'll go a little bit further into this, but I kind of want to skim through this because this isn't fully what you're being tested on. It's just more, again, the foundations of it. So frequentist interpretation is everything is a relative frequency, and the probability is that a proportion of the times the outcome will occur out of a random process rather than something else. Okay. The probability of large numbers states that as you observe more and more of the same criteria, the same variable, the proportion of the occurrences of a particular outcome will basically come down to a certain outcome that is kind of definite after X amount of time. So, for example, if you flip a coin 10 times, there's going to be 4 heads. Okay, that's kind of not surprising because, you have a 50% chance every time. But if you flipped a coin 100 times and you only got 4 heads, whoa, the probability of that is actually pretty pretty influential. I don't even say influential. It's pretty significant is what we'll use. Now, what if you flipped 10,000 times or 1,000 times and you only got 4 heads? Whoa, that's a lot. The probability of that is extremely small. So this is in your book. I'm just going to skip by this because it will throw you off on the analogy that I just gave or the example that I just gave. But I will show it here, a better one in here in a second. So the probability of large numbers, I'll actually show you here, and this is the proportion of smokers in the same sample, plotted after 10,000 samples. So when we look at this, it's showing 2 different trials of something. So basically, let's just say one researcher wanted to find out how many individuals were smokers, and then another researcher also wanted to find out how many smokers. So they both go out there, and if you see trial 1, let's just call them researcher 1, the first person that they asked, are you a smoker? They say yes. Okay, awesome. Well, then so far 100% of the individuals that they have asked are smokers. Whereas trial 2 or researcher 2, they asked the first person and they were not a smoker. Okay, well then that's 100%. Now let's go over to that 5. So even on researcher 2, after asking 5 different people, none of them were smokers. It's still at a 0%. However, look at researcher 1. In fact, after their first initial person that they asked 4 more people. It just basically went down, 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 and down because all of them weren't smokers, or at least 4 out of the 5 weren't smokers. So it's actually giving you already a better understanding, a proportion or a percentage of how many smokers versus not. Now let's fast forward. These researchers have nothing else better to do but to ask people whether they're smokers or not. Well, it really comes down to, after enough sampling, that it comes to a probability of 0.2. So that's saying that 20% of the people that they have asked were smokers, meaning that 80% were not smokers. So this is the idea that, when you're collecting data, the more data, the better, because you'll get a better understanding. With the Bayesian interpretation of probability, it takes into account a subjective degree of belief. For example, if the same event is being observed twice, or observed by 2 different people, then you're going to have a slightly different, maybe a slightly different data set out of that. And so basically what this is kind of saying is, as someone else who needs to replicate the data you do, because that's where a lot of research comes, is that everything has to be done over, people have to be able to replicate it. And so this is taking that into account. In other words, I'm going to record a certain amount of data and I find a probability, but then someone else across the pond, let's just say across the ocean, they're also doing the same exact research that I am, but with different people. Well, the Bayesian interpretation is when you have to combine my data set and their data set, it's combining those and it's taking that into account that they're both different. So again, we're not going to go over this too much, but just to get an idea of where we are with science and research. Okay, for sample space, it's a collection of all possible outcomes for a trial. So, for example, let's just say a couple has 2 kids. What does a sample space for eye colors for these kids? And for simplicity, we're just going to assume that the eye colors can only be brown and green. And well, it's possible for both kids to have brown eyes. It's also possible to have both children with green eyes. But it's also possible to have one with brown, maybe the first one with brown and the second with green. Or maybe there's the possibility of the first child having green eyes and the second child having brown eyes. So it's putting all possible events into a basically sequence. So if you look at the bottom here, we have S equals, we have brown, brown, we have green, green, then we have brown, green, and green, brown. So those are all the possibilities based on this one example where only the probability of either green or brown eyes for the children. With random variables, the sample spaces and the events within a sample space include all randomizations, or the random variables. So a random variable is a real valued function that assigns a numerical value to each possible outcome of the event. So in the last slide, there was 4 different examples. What are the probabilities of each of those? Well, if we were just to kind of like put a big easy blanket over it, then we would say, well, there's a 25% chance of each because there's only 4. But it gets a little bit more complicated than that, doesn't it? It has to, right? Ooh. So we're going to look at it in 2 different ways. There's discrete random variables and there's continuous random variables. This lesson will primarily focus on discrete random variables. Yes, we will cover continuous, but that gets a lot more fun. So we'll start with discrete random variables. So this is something that can be discrete. So we've already just talked about how you can't have a discrete would be, as this slide it shows, is the number of kids in a family. You can't have 2.5 kids. It has to be by a full set of numbers or integers. Whereas continuous can be unbroken. It can constantly be swayed. So the example in here is the average weight of the simple random sample of newborns selected from a population. So notice that it even says SRS right here. So just want to point out that, hold on, I want to change it to a laser pointer. Yeah, there we go. All right. So it's saying that an SRS, all these have to be randomly sampled. So it's not that you're able to just take anything. It's that this has to be under the law of the laws of nature of randomization. Let's just put it that way. So the average weight of SRS, that can go down to a very minute, very small number. It can go from, 6.79824, so on and so forth. It can continue on. That's the difference between continuous and discrete. So with discrete variables, we are looking at the probability mass functions. And this is, it comes as a table, it comes as a graph, it comes as, it doesn't come as Santa Claus, unfortunately. But this is a mathematical relation that puts all of the possibilities into basically a set of discrete random variables. Whereas a continuous random variable is the probability density function, or PDF. Here's the difference between the two. Okay, there's really not much other than one is discrete and one is continuous. That's it. That's all you really need to know about this. Discrete is PMF, continuous is PDF. Voila. This is an example of both. So the top one is, this is the same exact graph, but one is as discrete and one is as continuous. The top one is discrete, or PMF, and the one on bottom is continuous, or PDF. So if you notice that the shading, that the shaded area, or that line, that's the area under the curve, the AUC. And basically that's showing the probability of everything from the very bottom of the number, the lowest number, all the way up. So it always travels from the left to the right. And for this, we're looking at the probability and the function of anything from 1-year-old, or I guess the 0-year-olds, to 9-year-olds. And this will have a certain number to it. So it will give you an idea of how far that is away from the mean. You can figure out the standard deviation of where that is, but you're looking at the whole area under the curve, whenever something like that is shaded. They come in all shapes and sizes. I'm going to briefly show this, but this is just to give you an idea that PDFs come in all forms. We'll talk a lot about the normal. We'll go over chi-squared. This is an exercise. I personally wasn't a fan of this example. It really kind of threw me off, but it makes sense the more you look at it. Mathematically, it makes a lot of sense. But I'm just like, why do we have a triangle? But it is something that, if you're really, urgent to learn more about PMFs, go to exercise 513. Okay, moving on. This is probably the main point in the entire chapter for chapter 5 that you need to know about probability distributions, is that there are 4 properties that go along with it. The first one is that probabilities are always in between, the probability has to be between 0, or it has to equal to 0 all the way up to equal to 1. In other words, going back to the example of the cigarette smoking, if we have a 20% probability of smokers in a population, then that means that the rest has to be 80. And so it's always going to be somewhere between that, right? So you're not going to have something where it's 20% are smokers and 81% are non-smokers. That would break the first property of probability distributions. Number 2, a sample space is all possible outcomes. The probability in the sample space is always an equal up to 1. So going back to the cigarette example, as I just mentioned, 0.2 plus 0.8 equals 0.1. Everything has to equal up. So just, in contrast to maybe property 1, where the example that I gave that you can't have 81% smokers and 20% or 81% non-smokers and 20% smokers, property 2 says you can't have 20% smokers and 79% non-smokers. Where's that 1%? That breaks the second property. Property 3, the complement of an event that is not happening is 1 minus the probability of that event. So in this example, it says the probability of a hat equals, this little hat right here it means it's the complement. So all you do is 1 minus the PR of A. So A represents the complement, not a hat represents the complement. In other words, let's put this back into our smokers example. So if we say that A is the probability of a smoker, that would be 0.2, then the probability of a non-smoker would be 1 minus 0.2, which is 0.8. Property 4, probabilities of disjoint events, which means that they cannot occur concurrently, that they can be added. So if they're disjoint, then you have to add them. So we'll go a little bit more into property 4 here a little bit later. I don't want to just toss all of the 4 fully at you. So here's some examples of the first property. The probability has to be between or equal to 0 and 1. So it's basically saying it's completely impossible if you end up having like a probability of 0.0 or 0.0. Done. That's it. Whereas if you were to roll a die, your probability looks a little bit different. So it's going to be, I believe, 0.167. It's actually 1.66667 or something like that. I don't know. You have the idea. It's pretty unlikely. It's a 1 in 6 chance. Flip a coin, you're right in the middle. That is a 0.5. And then you can go all the way up, and just if you get a 1 on something, then you are 100% positive. So I'm trying to give an example. If I run into a wall, the chances of me actually hitting the wall is 1. It could be 0.9999999, but that's I'm just going to round that up to 1 at that point. Something that obvious. It's a silly one. Hey, I was right on that. 1.66 repeating. This is just giving you the spectrum from 0 to 1 for property 1. There it is in fraction form. Yay! Okay, this is a subjective probability line. So basically, and this is also in your book, I don't want you to take this verbatim, but I do want to point it out in that it is a nice way to basically practice your wording. So say you were reporting something. Let's go back to our cigarette example. Then I could say actually, using this kind of like this formula sheet, you can actually say, rather than saying like, it's very rare that I'm going to find a smoker amongst the population. Well, using the term very rare is not necessarily the best one. And based on this exact example, it would actually be better to say something like, it's actually infrequent to find a smoker within the population. And again, this isn't like set in stone when it comes to these words, but it's a better way to actually understand something and actually practice your vocabulary. When would you say very frequent versus infrequent? Well, this will give you a better idea. Okay, this is a histogram of a PMF. A PMF is discrete. So notice that each of these, they're kind of separated out. That's okay. I know it's, that's usually a bar graph kind of thing, but with a PMF, it's just allowing you to kind of space out the number of successes, which is fine to still separate. It's still technically a histogram. It's kind of technically a bar graph as well. This provides just a little bit of explanation of each property. So if I was actually to add up these 5 properties, so and let's just explain what this is real quick. This is the probability of a success of patients. That we have 4 patients. The probability that if they were to all go through a certain procedure, what is the likelihood of the success for all of them? So, and I think for this example, it's a 75% chance that it's going to be successful. So using maths and finding the probability of that, you can actually, it actually shows that the probability of no one surviving from that procedure is highly unlikely. It's less than 1% chance of that happening. Because if you have 4 people and there's a 75% chance, it's actually, if we go back to this one, it's pretty frequent that people are going to have a successful procedure. Now, the chances of only one is 4.7%. The chances of 2 successes is 21%. The chances of 3 is 42, and to have everyone have a successful chance, that's actually, it goes a little bit down to 31 or 32%. So this gives you an idea, and honestly, this is something that you can really play with. If this isn't like really, the light bulb isn't kicking on, this one takes a little bit of practice. So just, bear with it. But again, if you were to add all of these up for notice that for property 1, all of them are between 0 and 1. Sample space, if you were to sum up each of these, it would equal to 1. The complement of each of these not happening is 1 minus the number. So, for example, the chances of this one is 0.4219. If I do 1 minus 0.4219, then I would get the complement of 3 successes. And for property 4, that is where probabilities of disjoint events can be added. These are disjoint events because each individual patient is not related to one another. So if one has a procedure and doesn't make it, that's not going to impact the 3 remaining patients. All right, so we've gone through property 1, now we're on to property 2, but we've kind of covered it, and I'm sorry, they just keep on popping up like ghosts. I don't mean to. So let's get to property 2, or at least the next slide. Let's see what we have here. So this is actually the explanation that was just provided, as well as the graph, and it's 75% of the time. I kind of don't need to go over this, but this is the PMF. This is a PMF right here. This little table. It's nothing intimidating. All it is just showing you the probability of X of successes. So if you put in that lowercase x into this lowercase x, it would say the probability of 0 successes, the probability of 1 success, the probability of 2, 3, and 4. Okay, we're going on to the complements. How complementary? Haha. Okay, so the example that we provide here is if you have, actually, let's see if we can go. Okay, if we have A, the probability of hat A is 1 minus the probability of A. So for this, it would be 1 minus 0.3164. So that equals to 1 minus 0.3164 is 0.6836. That's all it's saying. Let's do another one. Oh, sorry, excuse me. Which all of that is equal to, ta-da, the rest of these. This is the complement of it. All right. If you were to add that up, and let me just do the math on that. Yep, that's about right. Sweet. So that's the complement. All right, and we are on to the last one, which is disjoint events. So again, I already explained it. I don't really need to, I guess I can kind of take it home with this, is that if we have A, B represent 4 successes and B represent 3 successes, since they are both disjoint, you can actually combine the two and you can say the probability of observing 3 or 4 successes is equal to 72% or 73%. So basically what this is saying is with property 4 is that I can take 2 of any of these, or maybe even 3. I can say what is the probability of observing 2, 3, or 4 successes? Well, then I would add up this one, as well as this one. And then my chances of actually having any of these 3 is pretty darn high because we already know that this one is low. This almost seems common sense now that when you really look at it, because honestly what this is doing is just taking or giving one way or the other. That's really where probability is when it comes to these examples. There are more properties for this because why not? And I'll be honest, this isn't something that I'm really going to hone in a lot and really try to trick you on it, because it can get kind of sticky on like, wait, where am I on stuff? And so I'm going to go through it. We'll practice it a bit, but we're going to move on with it. But it's really important just to know that everything is based on probability, and knowing those properties is incredibly important. So we'll just go over some main points here. So for independent events are 2 processes that without knowing the outcome, or if knowing the outcome of one or the other has no meaning for the other outcome. So for example, if I was to toss a coin and it either chooses heads or tails, those are independent of each other. Outcomes of I'm sorry, let me try that again. If I was to toss a coin twice, the first outcome really doesn't matter to the second outcome. It's a completely different one. Just back to my original example with the 4 patients is that just because one had a successful event doesn't mean that the next one's going to be successful. That is an independent event. Now, in contrast to that, that is a dependent event. And that is the good example that we have in this is a deck of cards. So if I was to draw 2 cards from a deck, well, by me taking the first card, and let's say it is an ace, and I don't replace the card or shuffle them or anything, the chances of me getting an ace, for instance, on my second draw is going to be less because I already drew an ace. So each outcome is dependent on the prior as well as the future outcomes for certain events. All right, let's go back to independent events. You toss a coin twice. What is the probability that you're going to get 2 tails in a row? So this is independence. We're checking for independence. So if I toss it once, bam, it's going to be, let's just say it's a 50% chance it's going to be heads. What's the chance that it's going to happen again? That's 50% chance as well. So we need to multiply that. So we would do 0.5 times 0.5, which is 0.25. They are independent of each other, and this is basically the product rule for any independent event. The general rule of addition is the probability of A or B is, in fact, the probability of A plus the probability of B minus the probability of A and B. So for disjoint events, this can happen at the same time. The examples we have here are rolling a die, rolling a 6 or a 2. So what is the chance of rolling a 6? Well, it's 1 out of 6, or 1.67. What's the chances of a 2? Well, it's also 1.67. Drawing a jack or red card from a well-shuffled card. We'll go over these here examples here in a second. So here we go. What is the probability of drawing a jack or a red card from a full well-shuffled deck of cards? And notice we say full well-shuffled. That's our randomization, right? Like we have to basically state and explain maybe somehow, especially when you're writing like how that randomization went about. So for this, what are the probabilities of either a jack or a red card? Well, first off, how many jacks are there? Well, there's 4 jacks, and we highlighted them in blue. And then, what are the probabilities of red? Well, we have all of these right here, and that's half of the deck, right? And there's a little bit of overlap with just 2 jacks. So that is the difference of a dependent, a dependent, I don't want to say dependent variable. I almost did. This is disjoint. It's a dependent event. That is what I meant to say, dependent event. So for this, what does this look like? Going back to that previous slide, we are going to add all of these and all of these, and we're going to minus whatever that is total. So what does this look like? We have the probability of jacks plus the probability of red minus the probability of jack and red, which is we have 4 out of 52, which is blue, plus 26 out of 52, and then we minus 2 out of 52. So this is just simply stating what is what is that merge of that color, and that's just 2. So we have 26 plus 2 minus 2. Oh, I'm sorry, excuse me. 26 plus 4 minus 2 divided by 52, and that is 0.358. If I went over it and I confused you, just simply mute me and just look at that for a bit. And this equation should just make sense, hopefully. If not, ask. Okay, going on to another property of adding probabilities. It shouldn't say property 4. I'm sorry, that was from the prior, but it is a property nonetheless. So when 2 events are disjoint, the probability that A or B will occur in the sum of the probability. So again, this is just going back to the probability of this and this equals something. So this actual example right here, notice that there is no merge, just like that last example. There is no deck of cards and something where I'm asking red and blue. In this example, the probability of having both A and B, well, just based on this visual, because they're separate, it's 0. That's all this is saying. So this is mutually exclusive for disjoint. They cannot happen at the same time. The outcomes of a single coin toss cannot be a head and a tail. That's all this is saying with adding probabilities. So, as an example, what is the probability of drawing a jack or a 3 from a well-shuffled deck of cards? Well, we know that this is 4 divided by 52, right? And this is 4 divided by 52. Well, what would we have to do? Subtract something? Do we need to add something? They're completely disjoint from each other. Unlike the last time where there was crossover, we're not having to do that. So in other words, all we need to do is just add the probabilities of both. And what is the probability of drawing a jack or a 3 from a well-shuffled deck of cards? It's about 15% chance. Let's look at a 6-sided die. A die is rolled. What is the probability of rolling a 6? I've already gone through this. It is 1.67. We're rounding up right at the top there. Okay, what's the probability of rolling a 2? Same exact thing. Nothing has really changed, just the number that we were actually hoping to potentially roll. What is the probability of rolling a 6 or a 2? Okay, what are we going to do here? I'm questioning my life now. What do I do? Is it this one or that? Well, we just add, so it's not too bad. We would just add 0.167 plus 0.167, and that equals to 0.33. We can also do it in fractions. Here it is. Calculate the percentage. Bam. What is the probability of either getting one number or the other number? 2 out of the 6. So let's try another one. What is the probability of rolling a 1, 2, 3, 4, 5, or 6? This is just like running into a brick wall. It's a 1%, or it's a 1%. It is a 100% chance that I'm going to hit my head on it. It is the sum of all of those equals exactly to 1. All right, let's have a little bit more fun. Let's mix it up in a bag here, shall we? Let's say we have 29 items. Why did we choose 29? I have no idea. I apologize. It's a random number to do. Pretty sure it's a prime number, which makes it even more fun, right? So we have 8 green cubes. We have 9 green discs. Why are they discs? I don't know. We have 5 yellow cubes, and we have 7 yellow discs. So 2 different colors, 2 different shapes, but overall we have 4 different types of objects that we can hold in our hand. All right, what is the probability of us drawing a cube out of this bag? Well, what will we have to do? We would basically add the fractions together to get an idea. So for this example, we're just looking at the cubes. We would want to get 8 plus 5 out of the total of 29. So that's 13 divided by 29. It's a 44% chance, 0.44 proportion, that you will pull out a cube. Okay, what is the probability of drawing a yellow item that is a cube and discs out of the bag? So we add 5 plus 7, that's 12. So 12 divided by 29, that's 41%, or 0.41. What is the probability of us drawing a yellow cube out of the bag? Just that. It is 5 divided by 29. Am I right? Haha, totally right. All right, and lastly, what is the probability of us drawing a yellow item or a cube out of the bag? So we're going to have to grab all the yellow as well as the cube right here. So we're going to add 8, 5, and 7. Okay, so if we have this is the 5 plus 7. This is the yellow item right here. Excuse me. And then we have the 13. We're going to add the 13 because this is all 13 cubes total. Now, this is, if you didn't notice already, this is a non-disjoint event, meaning that there is some crossover in the question that we have. What is the probability of us drawing a yellow item or a cube? Whereas all the prior examples, that they were at least able to be separated, this is the first one where we're actually like merging. So imagine those two, we had that example where there's the red circle and the blue circle. They weren't touching, those were disjoint. But now this equation, we're actually combining a little bit and we're looking at what is right in the middle. So we have the 12 items plus the 12 yellow items plus the 13 cubes minus the 5 yellow cubes. So we're subtracting so we don't add up the same exact thing over again, because these 5 yellow cubes all have already been accounted for within these two right here. All right, the answer is 20 divided by 29, which is 0.69, or 69%. Another property is conditional property, and that is denoting that the probability of, say, B is true given that A is evident, and this is only as long as A is greater than just 0. So going a little bit further with that, so start with the definition of conditional property, and this is the same exact thing that on the last slide, and then if you rearrange it, you can actually make basically what this is a multiplication rule. So rule 7 and 8, you can look more on this within your book. It gives you better examples, and I believe it's with dogs. So in dogs and cats, and who doesn't like that? Let's say you have 10 poker chips in a bag. The first 5 are red, the next 2 are blue, and the next 3 are green. So what is the probability of drawing an even and a green chip? So we need to find the probability of each of these equations, which relates back to rule 7 and 8. The probability of the even numbers is half of them, is half of 10, so that is 0.5 or 50%. And the probability of green, there's 3 out of 10, so you do 3 divided by 10. So the probability of green and even, so which really just narrows it down to 8 and 10, that's just 2. So it's 2 divided by 10. So that is the general rule of it. It's multiplication. You can just look at it the same way. And that's rule 8. Now, when it comes to rule 9 and 10, it goes into more detail that is kind of beyond the scope of what I really want you to practice with this, because we're going to do a lot more as the semester goes on when it comes to things. But really, at the end of the day, what we need to know about is the probability of something happening versus the probability of something not happening. And we went over in a very general sense, because I really actually want to spend more time with actual data sets than drawing out more rules and things like that. So I hope this helped. Thank you.